This section will briefly outline the water quality of the influent seawater and effluent product water and brine discharge. Since the intake will be open ocean, the water quality will be highly variable depending on local pollution sources and time of year. The major difference with open ocean intake is the amount of solids that will be entering the plant. There are a few other water quality characteristics that will be investigated, including temperature, pH, dissolved oxygen, and salinity concentration. Discharge water is broken up into brine and product water. Brine water will be high in salinity and solids, roughly double the influent salinity concentration, while product water will be completely potable. Due to the inability to take and analyze water samples, averages are assumed to be the water that San Onofre Desalination Plant will be treating. These averages are based on previous studies, reports, and online data that can be publicly accessed. The San Onofre Desal plant will treat open ocean intake seawater to produce potable water for human consumption. This process will involve filtering suspended solids and removing dissolved solids from bacteria in the water. Due to the difficulty in removing dissolved solids such as salts, a reverse osmosis process or RO process will need to be utilized. However, in order to prepare the water for reverse osmosis treatment, a few steps will need to be taken before passing through the RO membranes. Additionally, due to the removal of almost all constituents from the water after RO treatment, post-treatment will be required before distributing the water. The overall treatment process will consist of pre-treatment, microfiltration, reverse osmosis, and post-treatment. The figure in this slide presents the process scheme diagram. Pre-treatment is the first step in the seawater reverse osmosis process. This process will involve the treatment of larger particles and colloids. By doing this, we minimize the amount of particles being treated in the subsequent processes and avoid a system failure due to fouling or clogging. This is accomplished by physical and chemical processes. The physical process involves vertical traveling screens and arcal filtration, while the chemical processes involve biological activity removal and pH adjustment. Microfiltration is the next process involved with the seawater treatment. This process prepares the water for RO treatment by filtering out small particles and bacteria, which increases RO efficiency and prevents fouling. Microfiltration is accomplished by pressurizing water into a tube, where the particles and contaminants are then strained through tiny hollow fibers as small as 0.1 micrometers. This also removes bacteria such as Cryptosporidium, Giardia, and Legionella. Product water is sent through to RO treatment, while captured particles are removed with the discharged water. For this design, PAL Corporation Microsa LGV modules will be used. The RO process is the keystone portion of the seawater treatment process. This process filters out all suspended solids and the majority of dissolved solids. RO is implemented through the use of membrane technology filters, which remove molecules and ions from the solute. This is achieved by applying a force to a solvent in excess of the osmotic pressure. This forces the solvent from a region of high solute concentration through a semi-impermeable membrane to a region of low solute concentration. For osmotic pressure to be exceeded, high-pressure pumps must be used to pressurize the water from 600 psi up to 1200 psi. The membranes used are comprised of a dense layer of polymer matrix and are usually designed to allow only water to pass through. Therefore, these membranes are ideal for preventing the passage of solutes such as salt ions. Ultimately, this process results in two forms of product water, one with a high salt concentration and one relatively salt-free. For this plant, we will incorporate a two-pass split partial RO system. To determine the necessary parameters for our treatment, IMS design will be used. This is a program provided by Hydronautics that allows the user to determine the most efficient membrane combination while evaluating all necessary parameters for design. After evaluating 4 different membrane combinations, we determined that the SWC6 and SPA2 Max by Hydronautics is the most efficient. The purpose of post-treatment is to prepare the water for distribution after filtration. Although reverse osmosis is an effective barrier to pathogens, post-treatment provides secondary protection against compromised membranes and downstream problems. Because of the water pH and the salt's content after RO, it is not adequate for human consumption, and it is necessary to add calcium hydroxide to adjust the pH. To avoid post-contamination during storage of water, sodium hydrochloride is added. Thus, the 3 parameters considered in post-treatment are remineralization, pH adjustment, and disinfection. Shown in this slide is the overall process flow diagram for the San Onofre plant. This figure incorporates the flow at each process as well as the influent and effluent flows. These flows are based on recovery efficiencies, design flow flux rate, shapes that are cylindrical represent tanks, while the rectangular shapes represent processes such as MF and RO. Chemical additions used during pretreatment and posttreatment are not shown in this figure, but can be found in their respective sections. It can be seen in this figure that the product water flow successfully reached the 55 mgd mark that the project aimed for.
There are many structural components involved in the design of the San Onofre desalination plant. One of the Bad Boys and Associates' main focuses was the design of the clear well tank. After a comprehensive study of existing desalination plants with similar design capacities, a 5 million gallon clear well tank will be sufficient for the plant, which is designed to produce 55 million gallons a day. If the plant is going to be expanded to produce over that, it would be necessary to add another clear well tank. According to a comparable DYK 5 million gallon tanks, the cost is estimated to be $2,250,000. This includes the cost to design and build the tank. The diameter of the tank is 168 feet with a maximum water depth of 30 feet. The tank will have a total of 37 columns with a spacing of 23 feet on center. The columns are 30 inches in diameter and will be reinforced with 8 number 5 steel bars. It is also spirally reinforced with a 2-inch spacing and will sit in a 10 foot by 10 foot square footing. This is to accommodate for such a heavy roof. The roof will be a flat slab, poured in place, reinforced concrete roof, which will be in accordance with ACI 350R. The roof is to have a minimum thickness of 50 inches at any given point. In addition to the clear well tank, Bad Boys and Associates have designed the building to house all the various processes of the desalination plant as well as its employees. Since they are planning on to build such an important structure in California and location near 2 fault lines, it is important to consider the seismic forces that will act on the building in the event of an earthquake. In order to resist the effect of the seismic forces, we choose a structural system listed in the ASCE 705, Table 12.21, the Seismic Forces Resisting Systems, or SFRS. This system will act as a guide for vertically oriented structural elements above the foundation that are expected to act together to resist earthquake forces. Our typical building to house the elements of the desalination plant will be a simple steel structure. Spacing between columns will be 15 feet. The beams used to span these gaps will be W21 by 48 steel I-beams. The column sizes will be W21 by 48 for the larger buildings and W16 by 40 for the smaller buildings. For our roof design, we wanted a design that was simple because of the limited requirements from the building. The buildings will only be used as a cover from weather for multiple desalination operation processes. Knowing the minimum requirements for our structure, we chose to use a simple king truss with prefabricated light gauge steel truss. The advantage being that it offers a high strength while still lightweight roof system that is easy to install.
After reviewing the soils report for our designated site, we decided that the best foundation method for the simple steel buildings would be to drill piles into the bedrock. Since San Diego is located near 2 earthquake fault lines, an earthquake is always a potential threat to building integrity. By drilling the piles into bedrock, we ensure a higher factor of safety if a catastrophic event occurs. The foundation system will use multiple piles at spacings of 25 feet in each direction with piles on each corner of the building. This is done to ensure that the load is distributed evenly across all of the piles. The piles will be end-bearing piles with a diameter of 1 foot and embedment depth of 4 feet into the bedrock. To reduce the damage that the piles incur during construction, we will first pre-drill to the depth of embedment and then use concrete to solidify the pile into the bedrock.